3.6, rational functions and their graphs. We don't do a whole lot with polynomials, as I just said in this class, but we kind of have an idea of what polynomials are. Certainly quadratic expressions with x squared terms and x terms and constant terms are polynomials. We may encounter a few higher degree polynomials as they're used to build these rational functions, maybe with an x cubed term or an x to the fourth power, x to the fifth power. Basically, if we take a polynomial expression, put it in the numerator of a fraction. Take a non-zero polynomial expression. If we just throw away the number 0, we have lots of polynomial expressions to choose from. Put it in the denominator of a fraction, we've got ourselves a rational expression. If we define a function, f of x equals p of x over q of x for those polynomials, we've got ourselves a rational function. There are some key properties of rational functions which differ from properties of polynomials. We want to look at the domain of rational functions. For polynomials, it's all real numbers all the time. For rational functions, sometimes there are numbers that can be substituted for x that make the denominator 0. We want to make sure to exclude any numbers that make the denominator 0. Sometimes, even though there's an x in the denominator, there's no number that can be substituted for that x to make the denominator 0. So the domain might be all real numbers, but in cases where there are exclusions to be made, we want to do that. So the domain also will look at asymptotes, lines that the graph of the function seems to be approaching. Sometimes it'll cross them, sometimes it won't. But we'll get to that in just a little bit. Some examples of rational functions. Take a polynomial numerator, polynomial denominator. What makes the denominator equal to 0? Well, set it equal to 0, solve for x, and find out. Hopefully these won't be too stressful for us. A little bit of factoring, but it's really not heavy-duty factoring. X minus 10 times x plus 2. I think we'll get that one done. If you were to FOIL that, you'd get negative 8x in the middle, negative 20 on the end, and x squared in front. So I think that's the factored form. What numbers make that 0? I'm thinking 10. I'm thinking negative 2. So these are the bad values of x, a couple of them. We want to write the set of all good values of x. So to exclude these, it's a little bit of a pain, because we have to say everything to the left of negative 2, we've got negative 2 and we've got 10, everything to the left of negative 2, everything between negative 2 and 10, and then everything to the right of 10. So it's the union of those three intervals. Like that. Most of the time when my math lab asks you that question, it will put it in the form of a multiple choice. So you can just kind of look at several different unions of intervals and see, okay, which one excludes the right values of x. G of x, as I kind of mentioned there, is going to have all real numbers in its domain. You said x squared plus 3 equal to 0. X squared would have to be negative 3. X could be plus or minus I times the square root of 3. So there are a couple of imaginary numbers that make the denominator 0, but we're just wondering, what are the bad real numbers? And if the only bad numbers are imaginary, all real numbers must be good. So pick a real number, any real number, square it, add 3, you don't get 0, so it's going to be in the domain. All real numbers are good. The h part, basically, or the h function, basically, I included this because it doesn't strictly fit the definition of single fraction, polynomial in the numerator, polynomial in the denominator. This fits that description. 3x minus 7 is a polynomial. X squared minus 11x is a polynomial. But then there's this 2x plus 3 that's added to it. The question would be, even though it doesn't fit the specific definition, could we put it in the form if we wanted to? It turns out we can't. All we'd have to do is get a common denominator. It wouldn't be pretty, but we'd get a common denominator and actually add the 2x plus 3 to that fraction in the box, and we could write it as a single improper fraction with a polynomial numerator, polynomial denominator. So it fits the definition. What is the domain? Can you factor x squared minus 11x? How do you factor x squared minus 11x? Take an x out. X times x minus 11. So you said x equal to 0 and x minus 11 equal to 0, and so x could be 0 or 11. So it's everything that's less than 0. These are bad values. 0 is bad, 11 is bad. Everything else is good. So those that are good are everything to the left of 0, everything between 0 and 11, and everything between 11 and positive infinity. Those are the good values of x. All right, need to look at the pictures. What do the graphs of these rational functions look like? Well, polynomials tend to look like that. Maybe a straight line, maybe a parabola. If you up the degree a little bit, you might get the polynomial to look like that. Generally, except for the straight lines, nice smooth curves for these graphs of polynomials. No holes in the graph, no gaps, no discontinuities. You can draw it, if you can reach that far, from negative infinity to positive infinity without picking up the marker. So, it's a little bit different when it comes to these rational functions. Maybe the simplest non-trivial rational function is this one that we're calling f of x equals 1 over x. Didn't spend a whole lot of time in that section with the library of functions, given these names. This is the function that takes a non-zero number and gives you its reciprocal. Call it the reciprocal function. F of 2 is 1/2. So you input the 2 and it outputs the reciprocal of 1/2. F of negative 4 is negative 1/4. Reciprocal of a negative number is a negative number. What is f of 2/3? Well, we're hoping it's 3/2, but it is, because it means take 1 and divide by 2/3, but that means take 1 and multiply by the reciprocal of 2/3, which is 3/2. So you input a non-zero number. Why can't we input 0? It's undefined. 0. 0 is not the domain. 1 over 0. That's undefined. So input a non-zero number, and it outputs the reciprocal of that number. So let's plot a few points. 1, 2, 3. 1, 2, 3. Negative 1, negative 2, negative 3. Negative 1, negative 2, negative 3. What is the reciprocal of 1? 1. So we plot the point 1, 1. We know the reciprocal of 2 is 1/2, and the reciprocal of 3 is 1/3, and the reciprocal of 4 is 1/4. And if we pick larger and larger positive numbers, the reciprocals become smaller and smaller. The reciprocal of 10 is 1/10. The reciprocal of 100, go way to the right, is 1/100th. So, as we go to the right, the graph will slowly but surely approach the x-axis. I say surely. Basically what that means is as it approaches the x-axis is you can tell me how close you want it to be to the x-axis. It's never quite going to get there. But you tell me how close you want it to be to the x-axis. And I can say, okay, well, as long as you're this far to the right, I can do a calculation, but as long as you're this far to the right or beyond, you're going to be at least that close to the x-axis, or no further from the x-axis than that. So it approaches the x-axis. We say that the x-axis, what's the equation of the x-axis? It's a horizontal line, all of whose y coordinates are equal to 0, right? All the points on the x-axis have different x coordinates, but they all have a y coordinate of 0. So the horizontal line, basically I wanted to write horizontal asymptote. Good ways to abbreviate that, not so good ways to abbreviate that. HA is a suggested way to abbreviate horizontal asymptote. Y equals 0. Basically, the graph is approaching that horizontal line. It also does that to the left. It approaches the same horizontal line. The reciprocal of -1 is -1. The reciprocal of -2 is -1/2. The reciprocal of -3 is -1/3. And it approaches like that. It approaches the negative, whoa, slipped there, negative x-axis from below, but nonetheless, it approaches the x-axis both ways. So all it would take, according to the official definition of horizontal asymptote, is for it to approach that horizontal line either to the right or to the left. But these rational functions, if they approach a horizontal line from one direction, they approach the same horizontal line from the other direction. So it does. What's going on between -1 and 1? What's the reciprocal of 1/2? 2. What's the reciprocal of 1/3? 3. And the reciprocal of 1/4? 4. How high does this graph go? What's the reciprocal of 1/10? Does it go that high? It goes as high as 10, sure. Does it go higher than that? Yeah, it will go as high as 100 or 1,000 or 1,000,000 or 1,000,000,000 or 1,000,000,000,000. Just choose a positive number close enough to 0, and you can make this graph go as high as you want it to go. It's unbounded above in any open interval containing 0, and it's unbounded below. You choose a tiny negative number, and it'll have a great big negative reciprocal. It's also unbounded below. When the graph of a function, or a function itself, is unbounded either above or below in an open interval containing a number, we say that vertical line is a vertical asymptote of the graph. So this one has not only a horizontal asymptote, y equals 0, but also a vertical asymptote, x equals 0, the y-axis, and we'll abbreviate that VA. Now, the Greek word from which we get asymptote literally means non-intersecting. It's maybe a little bit unfortunate that that's what it means. These rational functions are never going to intersect their vertical asymptotes because they tend to be undefined where their vertical asymptotes occur. But they can and often do intersect their horizontal asymptotes. So hopefully we'll be able to see an example of that. Oh, we need to look at the graph of g of x equals 1 over x minus 2. So let me clean some of this up. Going to get there using a couple of transformations. Highlight the first quadrant. I think that's where the key points are. The original graph here, f of x equals 1 over x, has what type of symmetry? It is symmetric with respect to the origin. Okay, and then just to review, does that make it even, odd, or neither even nor odd? Actually makes it an odd function. F of negative x equals negative f of x. Even functions have y-axis symmetry. The origin is not a point on the graph, but it's an important point, reference point for the graph. So here's the way I like to think of this transformation. We're going to take the point of symmetry, the origin here, and shift it 2 units which way? To the right. And then 1 unit which way? Up. So 2 to the right and 1 up. So the graph, this is not a point on the graph, but the graph, after we shift it 2 to the right and 1 up, is symmetric with respect to this, and the entire rest of the graph kind of comes along. Well, the asymptotes also are quite useful in helping us to see what's going on with the graph. If we take a graph that has a vertical asymptote and we shift it sideways, that vertical line will shift sideways. So We take the y-axis and we shift it 2 units to the right, and we get the line. X equals 2. That's the vertical asymptote of this. If we have a horizontal asymptote and we shift the graph up or down, that horizontal asymptote is going to get shifted up or down. This one gets shifted up 1. It was y equals 0 right on the x-axis. It goes up to y equals 1. And looks like that. I don't know. I'll give the arrows there. There we go. Y equals 1. The rest of the graph comes along. I guess I could plot 2 key points. 1, 1. If we go from 1, 1, 2 to the right and 1 up, we get the point 3, 2. If we take -1, -1, -1, -1, and go 2 to the right and 1 up, that takes us to the point 1, 0. If we then just complete the graph by working our way along the asymptotes to the top and bottom, right and left of the page, then we get a pretty decent graph of this. Something like that, something like this. If we wanted a little bit more precision, we could, well, we got the x-intercept. We could find the y-intercept, but that's pretty easy. Plot additional points if we wanted to, but this gives us a good idea of the graph. Main reason, I mean, it's practice with transformations, but the main reason I showcase this graph is that the next topic is how to find vertical asymptotes. How do we find them? Well, in this case, it's x equals 2. Notice 2 is the bad value of x. It's the number that makes the denominator 0. While that's not quite enough to guarantee a vertical asymptote, it's a great place to start looking. So when we're looking for vertical asymptotes, we're looking for numbers that make the denominator 0. There's an important exception we want to be aware of, but that's the key place to start. So how do we find them? Well, if we have our function and it's in lowest terms, take the rational expression that defines the function and make sure it's in lowest terms. Usually this means that we need to think about factoring the numerator, factoring the denominator, and checking to see if there are any common factors that we can divide out. Sometimes there are, sometimes there aren't, but we have to check. Make sure it's in lowest terms. If it's in lowest terms and there's a number a that we can substitute for x, like 2 in the previous example, and it makes the denominator 0, then x equals a is a vertical asymptote for that function. Reduce to lowest terms, and then check to see what numbers make the denominator 0. Those that do, I don't think I need both of those. Those that do are locations of vertical asymptotes. Let's look at example 3. (2x minus 3 over x squared minus 3x minus 10). Do you suppose that's in lowest terms? It may not be. So we have to check. Let's factor the denominator. Numerator cannot be factored. X minus 5 plus 2. Just check with me. Minus 3x in the middle, negative 10 on the end, x squared in front. These are the right factors. Now, with these factors, can we divide out a common factor? Can we scratch out the 2x minus 3 in the numerator and either one of those in the denominator? No. So, even though we could factor the denominator, all that told us was that there were no common factors other than 1. So it does turn out, although it wasn't obvious at the start, that it is in lowest terms. Now that we know that, we just look to see what makes the denominator 0. In fact, you can tell by inspection what makes the denominator 0, right? X equals 5 does. X equals negative 2 does. And since neither one of those numbers makes the numerator equal to 0, these are the vertical asymptotes. X equals 5 x equals -2. My math lab is going to want the equations, not just 5 comma -2. It's going to want x equals 5. That's the equation of a vertical line. X equals -2. Another vertical line. An asymptote is not just a number. It is it's a line, so we denote a line by an equation. So be sure to include the x equals part. Two vertical asymptotes here. A quick peek at the graph and just some similarities and differences between what the TI-83 Plus will do and what the TI-84 Plus will do. Oh, one additional thing, I've probably mentioned this in this class, the fraction feature, but just to recall, if you've got a newer version of the TI-84 Plus, if you press the alpha button right here, the alpha button followed by the y equals, it gives you this fraction menu. Number 1 on the list, n over d, I've got to believe that stands for numerator over denominator. But if you find it stands for something else, let me know. Number 1, you can actually enter the numerator of this, 2x minus 3, and the denominator, x squared minus 3x minus 10. Now, if you're using a TI-83 Plus, no worries. Doesn't have the fraction feature, or maybe even an older TI-84 Plus may not have the fraction feature. The thing to keep in mind is you want to enclose the numerator in parentheses, open the parentheses and type 2x minus 3, minus 3, and then press the divided by. The divided by serves as the fraction bar. Then also enclose the denominator in parentheses. It's going to be x squared minus 3x minus 10. Numerator in parentheses, press the divided by bar, denominator in parentheses, and you get a good look at this. Let's see if it just graphs the thing twice. I need a better viewing window. Need a much better viewing window. It is taking its sweet time. Zoom 6. Zoom 6. There we go. Now it's just tracing the same graph again. There it is. Do you see what's going on with the asymptotes? Pretty clear that x equals 5 and x equals -2 are the locations of the asymptotes, actually the asymptotes themselves. Right there, x equals -2, and right there, x equals +5. Now, if you're using the TI-83 Plus, what it will often do, as it's going through, it plots points. When it does that, the last point it plotted down here, it could even be below the screen, the last point it calculated, to give the appearance of continuity. Because although there's a discontinuity here at each of these asymptotes, to give the appearance of continuity, most functions that we graph are continuous at most numbers in their domain. It plots this point, maybe down here somewhere. The next one it plots is up there, and it feels the need to connect the dots so it appears that they're continuous. So if you see a jagged line like that, or maybe it almost looks like a vertical line in there on the TI-83 Plus, it's just the calculator means well by doing that to give the impression of continuity. It just turns out in cases where there's a glaring discontinuity, it puts something there that's not supposed to be there. So not a big, huge deal, but if you're just wondering why it does that, that's why it does that. So two vertical asymptotes. The B part, factor the numerator, x minus 3 times x plus 2. Factor the denominator, x minus 3 times x minus 4 is this one in lowest terms. Can we scratch out common factors? We can. The x minus 3s. We can scratch out, divide by x minus 3, divide by x minus 3. Now, at some point, yes. Oh, okay. At some point along the way, I will ask you the domain of a rational function. The domain of this one is all real numbers except 2. 3 is bad and 4 is bad. So if you're looking for the domain, find the domain before you reduce the rational expression. Negative infinity to 3, 3 to 4, 4 to positive infinity. But if you're looking for vertical asymptotes, a number that makes the denominator 0 like 3 may not produce a vertical asymptote if it also makes the numerator equal to 0. If we graph this, should be able to tell. I'm going to graph the original version here. Let's clear that out. But the x squared minus x minus 6 in parentheses divided by x squared minus 7x plus 12, and grab it. Pretty noticeable vertical asymptote at x equals 4. What's going on at x equals 3? Nothing really noticeable. It looks like it's going on its merry way. Plot a point with an x coordinate of 1, an x coordinate of 2, an x coordinate of 3, it would seem. And it's not until it gets close to 4 does it really begin to behave badly. Well, if we check it, if we evaluate the function at 1, we get negative 1. If we evaluate it at 2, well, we get negative 2. We wouldn't expect to get negative 3 if we plug in 3 because it's not a straight line. But we might expect to get something, but we don't. 3 is not the domain. The calculator, fortunately, instead of just flipping out and giving an error saying it's undefined, it just says nothing. There's no number you get when you plug in 3 because it's 0 over 0, and that's undefined. There's actually a hole in the graph that has an x coordinate of 3. If I try to show it to you, because it's so steep, it'll look like a great big gap in the graph. But you can get your calculator to simulate it if you change the x-min to negative 4. Basically, I'm just choosing the negative 4 so that I've got a negative 4 and a 10, and I believe the number 3 is halfway in between them. I think 10 is 7 units to the right of 3, and negative 4 is 7 units to the left of 3. As the calculator goes along its merry way, plotting points, it's hard to determine exactly what points it's going to plot, but it will always attempt to plot a point at the x value that's exactly halfway in between the x-min and the x-max. And if that's a bad value of x, you can get it to show a gap in the graph. There it is. Now the actual gap is really imperceptible. It's just a hole in the graph. The number 3 is missing from the domain, not that entire little interval there. But that kind of gives the idea that there's something strange going on at x equals 3. Anyway, the only vertical asymptote is x equals 4. But you want to keep in mind, reduce to lowest terms after finding the domain, but before finding vertical asymptotes. I like the way that sounded. I'm going to see if I can insert a text box and actually type that in. Reduce to lowest terms after finding the domain, but before finding vertical asymptotes. So we find the domain, everything but 3 and 4. Reduce to lowest terms, scratch out the x minus 3's, look for vertical asymptotes. X minus 4 is the only factor left in the denominator, and so 4 is the only number that produces a vertical asymptote. The non-vertical variety. Horizontal, also a slanted asymptote, or 2. Oblique asymptotes, we'll call them. There are 4 cases. The last case is really none of the above or doesn't have one case, so that was kind of easy. There are really just three serious cases that we have to consider for non-vertical asymptotes. Case 1. In all the cases, we take the rational expression, if it's not already in this form, and write it as a single fraction with a polynomial in the numerator, polynomial in the denominator. Like this one, or this one, or this one, or this one. That is, we don't want to have a polynomial plus a rational expression. We want it to be polynomial over polynomial, even if it has to be improper. In every case, we compare the degree of the numerator to the degree of the denominator. 1 to 2. Degree of the numerator is 1, degree of the denominator is 2. 1 is less than 2. Degree there is 2, the degree there is 5. 2 is less than 5. Case 1, we're finding non-vertical asymptotes. If the degree of the numerator is less than the degree of the denominator, I guess I said it right there, the graph approaches the x-axis. That's the only observation we have to make. The graph approaches the x-axis. The horizontal asymptote is the x-axis, y equals 0. Reason for that, for large values of x, the leading term of the polynomial dominates the polynomial. For large values of x, 8x is way bigger than negative 3. The larger x is, the greater the discrepancy. For large values of x, 7x squared is way bigger than 4x minus 5. So the larger the value of x, the more we don't have to consider the minus 3 and the 4x and the minus 5, and it just gets to be a war between 8x and 7x squared. But 7x squared is bigger. If you consider 10, you would have 80 over 700, which is kind of a small number already. If you consider 100, it's 800 over 70,000, which is tiny. We're not going to tell the difference between that y value and the x-axis. So for large values of x, the denominator dominates if it has the higher degree, and it drives the value of the fraction toward 0. Tiny numerator, large denominator, and it approaches 0. Quick peek at what happens when that happens. Let's look at 8x minus 3 divided by 7x squared plus 4x minus 5. Looks like a couple, maybe, of vertical asymptotes, but eventually it settles in and approaches 0 as we go to the right, approaches 0 as we go to the left. The other example, the one I usually actually do, is even more dramatic. There's just kind of a little bump close to 0, and then very rapidly, because the difference in the degrees is greater, it's a difference of 3 rather than just 1, very rapidly the graph, it kind of disappears into the x-axis. Case 2. The numerator and denominator have the same degree. Degree 2 in the numerator, degree 2 in the denominator. 2 equals 2. Degree 4 in the numerator, degree 4 in the denominator. 4 equals 4. When they have the same degree, neither the numerator nor the denominator dominates the other. And it comes down to the leading terms. 80x squared is going to be way bigger than 75x minus 1. 20x squared is going to be way bigger than 14x plus 71 once x is large enough. So those two battle it out. And for large values of x, the value of this rational expression is really close to 80 over 20. The x squareds offset each other, and it gets really, really close to 80 over 20. There's actually a particular value of x where it equals 80 over 20, and it crosses the horizontal asymptote. But it's the where did I say it? Right here. It's the ratio of the leading terms. 80 over 20. In this case, it's 10 over 6. Y equals 10 over 6, or 5/3. That's the horizontal line that it approaches. I particularly like the example here with the 80x squared plus 75x minus 81 divided by 20x squared plus 14x plus 71 I'm going to zoom 6. Does not have any vertical asymptotes. How long would it take for you to determine that 20x squared plus 14x plus 71 equals 0 has no real solutions? Couple minutes at most, right? Would it help to find the discriminant? Whoa, when did we do that? Like a month and a half ago? Discriminant? The discriminant works out to be negative, and so it means 2 imaginary solutions, no real solutions, and so no bad values of x. So you don't see any vertical asymptotes. But 80 over 20 means for large values of x, and you don't have to go that large to see it happening, it approaches y equals 4. 4 units above the x-axis, to the right and to the left. As you go way to the right, way to the left, the graph is approaching y equals 4. If you look to the right there, it actually, it's not clear in this viewing window, it actually crosses over the line y equals 4, goes up above it, and then comes back and approaches from above. It's kind of strange how it happens, but it actually does intersect its horizontal asymptote. Let's see, is there time? Sure there is, to talk about oblique asymptotes, slanted asymptotes. Case 3. If the degree of the numerator is greater, and not just greater, but exactly 1 greater, 2 over 1, 3 over 2, 4 over 3, 5 over 4, 6 over 5, exactly 1 greater. How to say this? 2 equals 1 plus 1, 3 equals 2 plus 1. Then the graph will approach a slanted line. All the examples I think I provide, it has positive slope. It could conceivably have negative slope, but it'll approach a slanted line, and the way to find it is to use polynomial division. I think in the minute and change that I have, I can use a little polynomial division down here. X minus 1, divide that into 2x squared minus x plus 2. We're looking for something of the form mx plus b up there, a linear expression. X times what equals 2x squared? It is 2x. Multiply 2x by x and get 2x squared. Multiply 2x by negative 1, get negative 2x. Change the signs and add. Remember doing that somewhere in an algebra class long, long ago? In a classroom far, far away. Or maybe it was this one, I don't know. There's a plus there. That's it was a plus, now it's a minus. So we get x plus 2. One more time through. X times what equals x? Plus 1. Now, if I shrink that down and calculate the remainder, is there time to shrink it down and calculate the remainder? I'm concerned that maybe there's not. What we'd get is a remainder of 3. But 2x plus 1 gives us the straight line. We'll go OA for oblique asymptote, the straight line that this function approaches. There's a slanted asymptote. The graph will approach a slanted line, maybe with negative slope, but I think most examples that I give you probably will have positive slope. We did the polynomial division real fast. For the other example, let's try it with this one. Let's give myself a little bit more space. The degree of the numerator is 3, and the degree of the denominator is 2. So for large values of x, to the right and to the left, everyone see the 3 there and the 2 there, and observe that 3 equals 1 more than 2. For large values of x, to the right and to the left, this will approach a slanted line of the form y equals mx plus b. Go with the darker blue there. And we just got to figure out what's the m, what's the b. And we use polynomial division to do this. In some cases, I think the previous case, synthetic division might have worked, but when the divisor is x squared plus 2x minus 3, synthetic division is not going to work. So we have to rely on the polynomial division. X squared plus 2x minus 3 Going to divide that into 3x cubed plus 2x squared minus 12x plus 10. X squared times what? Equals 3x cubed. 3x. Put 3x anywhere you like. I'm going to put it up above the x term, just because I like to put the x term up above the x term. I like to line them up, but if you want to put it in the first available spot, that's fine. Just be sure you multiply the 3x by all three terms in the divisor. 3x gets multiplied by x squared. That's 3x cubed. 3x times 2x is 6x squared, and 3x times negative 3 is negative 9x in a long division problem. At this point, we're supposed to subtract, right? Well, we could do that. Subtracting with signed terms, though, sometimes a little tricky, particularly when it's minus and negative and all that. So, with polynomial division, instead of subtracting, we do its equivalent to that. We add the opposite. In order to add the opposite, we have to change the signs and then add. Changing the signs gives us the opposite of those terms down below. Then we add them, and that's equivalent to subtracting the original terms. The negative 12x and the positive 9x combine, and we get negative 3x. The 2x squared and the negative 6x squared combine to give us negative 4x squared, and then a plus 10 on the end. And we repeat the process, well, just one more time. X squared times what? Equals negative 4x squared. Heard various things. I want to say negative 4. Negative 4 there. That way, if we multiply negative 4 by x squared, we get negative 4x squared. Negative 4 times 2x is negative 8x, and negative 4 times negative 3 is positive 12. We actually have the information we need for the oblique asymptote. So I suppose at this point we could simply say y equals 3x minus 4. I feel strangely compelled to finish the polynomial division problem, though, even though we don't technically need to. Changing the signs and adding, the minus becomes a plus, the minus becomes a plus, and the plus becomes a minus. So it's 5x minus 2. For the remainder, note the 3x minus 4 for the quotient and the 5x minus 2 for the remainder. Hopefully that's the way it appeared up here. It is. So we've actually rewritten, or it's actually possible to rewrite the rational expression as 3x minus 4 plus the remainder over the divisor. And all you need for the oblique asymptote is this right here. But if you're just wondering why does it approach a straight line, you just have to think what happens for large values of x. For large values of x, x squared, not only is it way bigger than 2x and minus 3, it's way bigger than 5x minus 2. So for large values of x, the value of this expression goes to 0. It's really, really small. So the difference between the graph of the rational function and the graph of this straight line, y equals 3x minus 4, gets really small. Get the calculator going, and we'll punch it in. I want to punch in the original expression, and then the graph, we'll graph the line, y equals 3x minus 4, and just notice in the upper right-hand corner, lower left-hand corner, not a lot of daylight in between the graphs. So let's see. Y equals 3. Let's see, I need parentheses. Open parenthesis, 3x to the third power plus 2x to the second power minus 12x plus 10. Close the parentheses and divide by x squared plus 2x minus 3. The standard viewing window is probably not going to be big enough to hold this, but I'll zoom 6 nonetheless. I think it's a little, actually not so bad there. That's kind of okay. We might ask the question, well, this has all but 2 real numbers in its domain. 1 is bad, -3 is bad, but everything else is good. So what's happening over here to the left? I think the graph is down below that. So let's go a little lower, maybe -30, and a little higher, maybe +20. And a y-scale of 5, and we can see a little bit better picture of the graph. There we go. So you can see what's going on kind of to the left, and in the middle, and to the right. If we were graphing this, what we would want to do is graph 3 different broken lines, dashed lines, the 3 asymptotes. There's a vertical asymptote, x equals 1. And we'd graph that, x equals 1. There's another broken line, x equals -3. Like that. And then there's the slanted line that appears to look something like this. And the equation of that line is y equals 3x minus 4. If we graph it, y equals 3x minus 4, it looks like that. Okay, so it's a good guideline with those asymptotes. Just a few key points plotted. Maybe an x-intercept, maybe a y-intercept, maybe one more point over here just to make sure it's above that line rather than below that line. Sometimes that happens. And a key point down here to make sure that piece of the graph is below the oblique asymptote rather than above it. And you can sketch a pretty decent graph of this rational function. Case 4 is simply an observation that if the degree of the numerator is at least 2 greater than that of the denominator, it does not approach a straight line as it goes to the right, as it goes to the left. There's not a horizontal asymptote. There's not a slanted asymptote. It might approach a parabola, just for fun, if you wanted to graph that function f of x that I have right here, or the function g of x. Actually, g of x wouldn't be that much fun. F of x is better. And zoom out a little bit, you can actually see that for larger values of x, the graph of that rational function actually begins to look like a parabola. The graph of y equals 2x squared plus 7. Example 4, last example, just to kind of summarize what we've been doing. Find the equation of the non-vertical asymptote. I think a couple of these have horizontal asymptotes. At least one has an oblique asymptote. Let's find them. I don't know if I want to take the time to graph them, but I may not be able to resist the temptation. The first one, the degree of the numerator is 1, and the degree of the denominator is 2, and 1 is less than 2. That means this is case 1, according to Mr. Mizell, for finding equations of non-vertical asymptotes. And so what is the non-vertical asymptote in this case? It is horizontal. Which specific horizontal line do we need here? Y equals... Well, we could memorize it or try to understand it. And if we try to understand it, we notice that x squared is going to be way bigger than all the other terms here. So for large values of x, the numerator is going to be tiny compared to the great big denominator, and that's going to drive the value of this fraction toward 0. So for far to the right and far to the left, the graph approaches the x-axis, y equals 0. Or just memorize it. Case 1, degree of the numerator is less than that of the denominator. It's the x-axis, horizontal asymptote. B part, degree of the numerator is 2, and the degree of the denominator is 2. And since 2 equals 2, it's actually case 2, not because it's 2's, but because they're the same. When the degrees are the same, what do we look at? It's horizontal also in this case, but it's not the x-axis. It's another horizontal line, in this case that's above the x-axis somewhere. For large values of x, kind of goes like this. Here's the thinking. For large values of x, 24x squared is way bigger than 51x minus 175. And 18x squared is way bigger than 41x minus 7. So the leading term dominates the numerator. The leading term of the denominator dominates the denominator. So for large values of x, the value of this fraction is not exactly, but darn near that. Large values of x. Mark it down. The value of the fraction is really, really close to whatever that is. But wait. The x squareds offset each other because they have the same value. If x equals 10, it's like 2400 over 1800. Plus or minus just a little bit. So the x squareds we can kind of look past and really boil it down. X gets large enough we can make the value of this function as close to 24/18 as we please. So, in lowest terms, what's 24/18? 4/3. 4/3. Now this one, it's kind of tempting to graph this. I know I've got other things I need to be doing. But if you graph 24x squared, come on, 24x squared plus 51x minus 175, close the parentheses, divided by 18x squared plus 41x minus 7, close the parentheses there. Just make sure I didn't type something unfortunate. That's probably okay. Zoom 6 again. Couple of vertical asymptotes it looks like. Does it look like to the right and to the left it's approaching the horizontal line y equals 4/3? Well, it's hard to tell. Maybe a little bit different viewing window. Maybe if I just went y min of about, whatever did I do? Y min of 0 and y max of 5. Maybe we could see the 1 1/3 a little bit more clearly. Does it look like it's approaching y equals 4/3? Well, it's kind of interesting if you have if your calculator has a good healthy battery and you've got a lot of time on your hands. Trace on the rational function and then start pressing the right arrow. If y equals 1/3, sorry, y equals 4 and, what is it, 4/3? 1 1/3 truly is the horizontal asymptote, it means we can make the graph as close, we can make the y coordinate of points on the graph as close to 1 1/3 as we want to by going far enough to the right or far enough to the left. Well, what is 4/3? If you want to write that as a decimal. 1.33. Right. So if we're patient and it holds out long enough, we do this long enough. Well, right now it's 1.3. You do it a little bit longer, it'll be 1.33. You do it a lot longer, it'll be 1.333. And the idea is, if that's the horizontal asymptote, if you're patient and your battery on your calculator holds out long enough, you can go far enough to the right to get as many 3s as you want to. Oh, and I suppose if you want to take a shortcut, you can just set the x max to what? What do you think the x max should be to give us 1.333? 100? I'm going to go bigger than that. How about 1,000? That might not be big enough, honestly. But I'm going to go there nonetheless. 1,000. So the graph looks really flat, and then it draws the horizontal line it seems to be approaching. If we press trace, still just 2 3s. 1.3329. And it looks like, there we go. Okay, I guess I wasn't far off. X equals, 1,000 would have done it. That's x equals 707 in that particular viewing window. So around 700 was enough to give us 3 3. So anyway, that's what's going on. For large values of x, we can make the thing as close to 4/3 as we want. And the C part, the degree The degree of the numerator is 2. The degree of the denominator is 1. 2 is exactly 1 more than 1. So, what type of non-vertical asymptote are we looking at here? Slanted one. Oblique asymptote. In the oblique asymptote, you can say OA, but be sure and say Y equals. Whether or not you put OA, it doesn't matter, but you must put Y equals, and then put X minus 6. For large values of X, it approaches a slanted line where the Y coordinates are 6 less than the corresponding X coordinates.
So there's two types of horizontal. There's one oblique.
Yes. It could be the x-axis, it could be a line that's parallel to the x-axis, or it could be a slanted line. These three types, non-vertical asymptotes.